All right, so here we go. When we're dealing with all of these rational equations and expressions that we've been working with, sometimes we get caught up in when are we ever going to use this? Well, today's the day. There are a lot of different types of problems that can be set up and solved using a rational equation. And so I picked out just a couple types, so we'll focus on these two types, but know that there's a lot of different types that of problems that use these. We're going to focus today on work problems and uniform motion problems. So let's start with some work problems. All right, so if you look at this scenario, it says that working alone, Kathy can paint a room in 5 hours. Leah can paint the room in only 3 hours. How long would it take the two of them to paint the room together? So I think the first thing to do here would be to make some sort of a guess as what we think would be a reasonable answer for this. So how long do you think, if they both were painting, go ahead and make a guess, how long do you think it would take them if they worked together? Okay, so some common answers that I see on this are, you might say 8 hours, you might say 4 hours, 8 from adding the 3 and the 5, 4 because there's 2 of them working. Some people guess 2.5, 1.5. It can be any number of things that I've seen. Let's go see what it is, and then we'll talk about your guess. Okay, so when we're doing these work problems, we always use this little formula: work is equal to the rate times the time. So how much work you get done is based on how fast you can work and how long you work. Okay, so it says here that Kathy paints a room in 5 hours. So the first thing we have to do is figure out what her rate is. In other words, how fast does she work per hour? Okay, so if it takes her 5 hours, then she could get a fifth of the job done in an hour. So that's like her rate. So we would write her rate as 1/5. And so likewise, if Leah were painting a room and she could do it in 3 hours, then how much could she get done per hour? Well, her rate would be 1/3 of the job. Okay, so basically what we're going to do with these problems is we're going to take all of the portion of the work that the first person does, add it to the portion of the job that the second person can get done, and together that should always equal one job completed. It always gets set equal to 1 because that's the portion of the job that we're going to finish. Okay, so let's set this up then. I'm going to start with Kathy. Okay, so remember that the work she gets done is her rate times her time. So right here, the portion of the work that she can get done, I'm going to take her rate times her time. So her rate was 1/5. And the question is, how long would it take them to paint the room together? Well, that's the whole question. What is the time that she needs to work to get this job done? So that'll be my X. Or really, let me undo that. Let's make that a T for time. Okay, now let's add to that the work that Leah can get done. Okay, so Leah's rate is 1/3, but they're going to both be working for the same length of time. They're going to work till the job gets done. So her time is also time. That's the rate times the time. And that's going to equal 1 completed job. Okay, so to clean this up a little bit then, if I take 1/5 times T, that's really going to look like a T over 5 plus a T over 3 equals 1. And that right there is the equation that we need to solve this problem. All right, so what I'm going to do is I'm going to come over here on the side, and I'm going to get a common denominator. If I look at this, it looks like my common denominator would be 15. So I'm going to take this times 3, and this one times 5, and this one times 15. And I'm going to write that as a 1/1. So I'm going to take 15 on top, 15 on the bottom. Okay, so if I move over here on the side where I have a little bit more room, I'm going to end up with a 3T over 15 plus 5T over 15 is going to equal 15 over 15. And remember, with these equations, we're trying to get that common denominator. Once we have it, we can take everything times 15 and the denominators will cross off. And so then I end up with a 3T plus 5T. Tell you what, let's go ahead and just add those together. What is 3T plus 5T? It's just an 8T. equals 15. Divide by 8. So t is equal to 15/8, or if we would change that to a mixed fraction or a decimal, it'd be 1 7/8. And then let's think about what we just found. T is time, so it's 1 7/8 hours. And if you recall, T was the amount of time I was going to have each person work and be painting. So that's the time that they have to work. And so when it says how long would it take the two of them to paint the room if they worked together, it would take them 1 7/8 hours. Okay, so let's talk real quick about what your guess was. The one thing that I want to draw your attention to is if you had maybe added the 3 and 5 and picked 8 hours. Maybe you added them and divided by 2 because there's 2 people, and then you had 4 hours. Neither one of those answers really makes sense, because here's the deal. If you look at this, Leah can paint the room by herself in 3 hours. By herself, she'd be done in 3 hours. So if you're guessing that it's going to take them 4 hours or 8 hours if they work together, well, that would be unfortunate. Kathy must be really bad because she's making it take longer than what Leah could have done by herself. So thinking about that common sense-wise, it certainly should have been under the 3 hours that Leah could have done on her own. All right, let's try another problem. Okay, on this problem we have 2 drain pipes coming out of this tank here. And if they're both running, then they can drain the pool in 3 hours if they're both going. So this time I know the time it takes for them to finish the job together. If they were both running, it would take 3 hours. Okay. Now, working alone, so perhaps one of the pipes is busted or something, you have to shut it down, and you're only going to be able to run one of the pipes. Okay, so it says it would take the smaller pipe 8 hours longer than it would take the larger pipe to drain the pool. Okay, but it doesn't really say how long it takes the larger pipe. The question is, how long would it take the smaller pipe to drain the pool by itself? Okay, so this time you're looking, instead of finding what it would take together, we already know that, we're looking at what would it take individually, time-wise. Okay, so here we go. We've got drain pipe 1. I don't know why I called it that. Let's call it the big pipe. And drain pipe 2 we'll call the little pipe. All right, we're going to figure out the work that the drain pipe, the big one, can do plus the little one can do is always going to equal 1 completed job. So for the big pipe, the work that it can accomplish is its rate times its time. Now the last time we knew the rate, this time we know the time. We're going to have that drain pipe running for 3 hours. To get the one job completed with both of them, it's going to take 3 hours. What I don't know is the rate. Okay, and so that's the same deal over here on the little pipe. I don't know the rate, but I know that the time would be 3 hours. We're going to have it running for that long. What it does say here, though, is that it would take the smaller pipe 8 hours longer than the larger pipe. Okay, so if I don't know how long it takes the larger pipe, I'm going to call that X. So if you remember earlier, when we said that Kathy could paint the room in 5 hours, then her rate was 1/5. So if the big pipe can drain the tank in X hours, the rate would be 1/X. So when you're doing that rate, that's where your fraction always comes into play. All right, so over here on the little drain pipe, we also don't know its rate, but it would be 1/, and this one, it said it takes 8 hours longer, so that would be X plus 8 hours. Okay, let's set this equation up. The big drain pipe, the work that it completes is going to end up simplifying to a 3/X, plus the work that the little drain pipe does is going to be a 3/X plus 8. And together, that's going to equal 1 completed job. All right, so then you have to do the algebra on it. We're going to find a common denominator. Looks like it's going to be an X and an X plus 8. And so take each of those times what's missing, and this one, which is going to end up 1/1, is X and X plus 8. All right, so then what I end up with for an equation, on the numerator, I'm going to distribute the 3. So I'm going to have a 3x plus 24. And then plus, on the next fraction, it'll get me a 3x. All of that is over my common denominator of x and x plus 8. On the right side, it's also going to have that common denominator of x and x plus 8. I'm going to go ahead and distribute in the top, and so when I take x times both of those, I'll have an x squared plus 8x. Okay, I've got this equation. I got both denominators the same. I'm ready to cross those off. I'm short on space, so I'm kind of crossing those off, but normally, remember, we write that. We're multiplying both sides by that common denominator. They go away. Okay, so on the left side, it looks like I'd have a 6x plus 24 equals, on the right side, x squared plus 8x. Since I have a squared term here, that's my clue I'm going to need to factor. So let's make this equal 0. Let's subtract everything over there. So x squared, if I subtract the 6x and subtract the 24, and then we're going to need to factor that. Remember, that equals 0 now. So that factors very nicely for us. Going to be a 12 and a, no it's not. It's going to be a 6 and a 4. A positive 6 and a negative 4. If you set those each equal to 0, you'll end up with an x equals negative 6 and an x equals 4. Now, a lot of the times we're going to get answers like this where you get two of them because you factored, but one of them doesn't make sense. It doesn't make any sense to have a negative value for x. Let's remember what x was. X was the time it took the big pipe by itself. Doesn't make sense to have it negative. So I cross that answer off, and I know that it's going to take 4 hours for the big pipe by itself. Notice, though, that the question is asking how long will it take the smaller pipe to drain the pool. I usually just cover my bases and I answer everything. The big pipe will take 4 hours if it's working alone, and the small pipe, well, it takes 8 hours longer. Okay, well that would be 12 hours then, if it was working alone. And there's your answer. Okay, so that's a couple work problems. Where the variable goes can vary, but what does always work out on these is you always add the two the two things that are working, add them and set it equal to 1 every time. Okay, let's try some of those distance problems, or the motion problems. Okay, so here's one where we have Drake who's driving 30 miles one way to make a sales call. He turns around, or I don't know if he's turning around, but he goes to his second sales call, and it's 35 miles from the first one, so he's going to have to drive 35 miles. He drove faster that time, 10 miles per hour faster, and it says if the total driving time was 1 hour for the entire trip, find Drake's driving speed on the way to his second sales call. Was he speeding? What do you think? I don't know. We'll see. Okay, so here's the deal. On these types of problems, we're always going to use our standard distance equals rate times time formula. That's how we set this up. And we're going to do a chart to help us organize all the information. Now, one of the things to keep in mind is that if distance is equal to rate times time, you could rearrange that formula and solve it for t or solve it for r. And in fact, what we're going to end up doing is solving for t here. And then notice that that's what creates a fraction, which is why this gets solved using rational expressions. Okay, so here's what I'm going to do. I'm going to take my information and fill in my chart. So it says here for the distance. On the first call, he had to go 30 miles. And his second sales call was 35 more miles. Okay, so those were the distances that he did. As far as his rate is concerned, we don't really know exactly how fast he went. We just know that he drove 10 miles per hour faster on the second one. Well, so let's call the first one R. That's the rate, or how fast he was going. And so the second call is 10 miles per hour faster. That'd be R plus 10. And that's really where we stop here. What we do from that point is we take this last set of boxes, the time, and what we're really going to do is we're going to use this relationship right here to fill in that box. So to find the times, all I'm really going to do is take the distance and I'm going to divide it by the rate. So right here, I know the distance and I know the rate. So the time is actually going to be 30 over r. And on the second call, the distance divided by the rate would be 35 over r plus 10. Okay, so we've got those two pieces of information. We're going to use those to create our equation. Now, there's one more piece of information we haven't used, and that's right here. It says, if the driving time was 1 hour for the entire trip. Oh, okay. So all of the time that it took on the first call, plus all the time on the second call, should add up to a grand total of 1 hour. Okay, well, there's your equation. Let's set it up. 30 over r plus 35 over r plus 10 is going to equal 1 hour. Now, this is kind of unfortunate that it equals 1. This is not like the work problems that always equal 1. That was a coincidence. I could have easily said it took him 5 hours for the entire trip. Then I would add these and set it equal to 5. Okay, so that just happens to be the total time. You add them, and it adds up to a total time. Okay, now before I get going on this one, let's talk real quickly about what another option would be. So in this case, they gave you a grand total. They won't always do that. Sometimes what they say instead is, hey, he spent the same amount of time doing this that he did this. In which case, instead of adding these up and setting equal to some grand total, what we do instead, if they took the same time here that he did here, we would just set these two times equal to each other and have our equation that way. That's just another option. Look for that to happen on your homework. All right, so let's look at this equation. So I'm going to try to solve this very quickly. All right, so common denominator is r and r plus 10. So this one times r plus 10, and this one times r. The 1 needs to be multiplied by both. And again, remember, this is really a 1 over 1, so I'll write it like a fraction. Okay, so what we're going to end up with then is, okay, this is kind of a longer one, so I'm going to kind of go down. I apologize. I'm going to be writing over those weird, all this pretty font stuff. Okay, so here we go. On the top, I'm going to have a 30r plus 300. I'm just distributing here, taking the 30 times both of those, plus 35r. And all of that is going to be over our common denominator of r and r plus 10. Equals, on this side, I'm going to go ahead and distribute the r through the parentheses. So then I'm going to have an r squared plus 10r, and that's all over the common denominator r and r plus 10. It's kind of messy, sorry. All right. So now that I have the common denominator of r and r plus 10, I'm going to take both sides times r and r plus 10, and they're going to cancel out. And all I have left is the numerator. So I'm going to bring this up here to the top and rewrite this, just the numerators. If I combine the left side, I'm going to have a 65r plus 300 is going to equal r squared plus 10r. Let's get everything over to the same side so I can factor. So r squared subtract the 65 is going to be a negative 55r. Subtract the 300 and equals 0. So now let's factor this. So kind of some crazy big number there. So factors of 300 that have a difference of 55. So one's going to be a positive, one's going to be a negative. So if you think about it for a little bit, see if you can come up with what would multiply to 300 but subtract to 55. Okay, you should have a 60 and a 5. It'll get you a negative 60 and a positive 5, and it also gets you negative 300. All right, so that means that r is equal to negative 5 or 60. Now let's go back and look at what was r again? R was the rate, the speed he was going to the first call. Doesn't make sense to have that be negative. 60 makes sense. Okay, so it would seem like he went 60 miles per hour on the first call. But really what the question is asking is how fast did he go on the second call? And so the second call was that rate plus 10, so that means on the second call he was going 70 miles per hour on the second call. All right, so that's a nice little example of how to do one of these distance equals rate times time problem in kind of motion. All right, we do set up a chart for these types of problems. All right, we're going to try one more. Okay, so on this one we have Stephanie. She's taking her kayak to the river. It flows downstream. Oh, the river flows downstream at 2 kilometers per hour. Okay, so that's great if she's going downstream because that's going to help her out. But if she's paddling, okay, and she paddled 15 kilometers upstream, then paddled downstream to her starting point. So she started off going 15 kilometers upstream, which means she's going to be fighting this current that is going here. So let's keep that in mind as we write this. Now, let's figure out how much of this chart we can fill in. It says she paddled 15 kilometers upstream. So that would be her distance, 15 kilometers. But the thing is she turned around and paddled right back to where she started. So even going downstream, her distance is still going to stay 15. Went the same distance both ways. Okay, so that was easy. Now let's look at her rate. The thing is she's paddling there. And sorry, I got ahead of myself. I'm filling my chart. Maybe we should look at the rest of this. It says the round trip took a total of 4 hours. Okay. Find the speed that Stephanie can paddle in still water. Okay, so she has her own speed that she can paddle, and then she also has the water that's going to help her or maybe hurt her depending on if she's going upstream or downstream. So what we're going to do is we're going to say that her rate is just R. That's her by herself, still water. If she's going downstream, she's going to do that, plus the water is going to push her an extra 2 kilometers per hour. So her rate really ends up being an R plus 2. So what do you suppose her rate going upstream is going to be? Well, this is her paddling really hard, but she's fighting that current, so it's going to slow her down. It's going to be minus 2 kilometers per hour. All right, so we have those 4 boxes filled in. So now we're going to come over here and we're going to fill in the times using this relationship right here. So for a time, the distance over the rate would be 15 over R plus 2. And the second one is 15 over R minus 2. So now what we have to do is we have to decide how to set our equation up. So I kind of hinted last time, you have 2 options. Either these 2 things are going to add up to a grand total of time, or these 2 times are going to end up being the same as each other. So we have to look back up at the paragraph and say, what's going on? Well, it says right here, if the round trip took a total of 4 hours. Okay, so I have the grand total of 4 hours. So this is not going to be one where these took the same amount of time. This is going to be one where you add the 2 times together and you've got a grand total of 4 hours. Okay, so here we go. Our equation would be 15 over R plus 2. Plus, going upstream, 15R minus 2, should be a grand total of 4 hours. I'm going to write it over 1. Okay, common denominator, R plus 2, R minus 2. And so on the last one, I got to do both, R plus 2, R minus 2. All right, so this is a little bigger problem, what we got going. Okay, so let's go ahead and work on distributing the 15 on both of those. So I'm going to end up with a 15R minus 30 plus 15R plus 30. All of this is over my common denominator, R plus 2, R minus 2. Over here it equals, also going to have a common denominator, r plus 2, r minus 2. But let's work on this numerator. I don't feel like this has happened to us very many times where we're going to have to do FOIL here. We're going to multiply those two together, and then we also have to take it times a 4. So often that just happens to be a 1, but now it's a 4. So we have to FOIL this together first, and then distribute a 4 through it. So if I'm going to do that, this r plus 2, r minus 2 foils together very nicely. It's really just going to be, and I'll write it up here, r squared, but when you do outer you get negative 2r, inner is a positive 2r, so those cancel. This is just an r squared minus 4. And then I have to take my 4 and distribute it through there. So my numerator here is going to end up 4r squared minus 16. Alright, so now you have your common denominator. Let's cancel those out, multiply both sides by that. You just have the numerator, so let's clean it up. On the left side, you're in luck, the 30s are going to cancel, so you get 30r equals 4r squared minus 16. Going to have to factor, so let's bring everything over. So 4r squared minus the 30r minus the 16 equals 0. Let's factor this. Actually, you know what I'm going to do? I'm going to pull a 2 out of that, get my numbers a little smaller. And then I can do 2r and r. And looks like I need an 8 and a 1. That'll get me a negative 16 and a positive 1. Alright, so my two rates would be a negative 1/2 and an 8. Okay, so sorry for this. You know, I think it's always fun to put colors and stuff in here, but sometimes it runs me out of room, sorry. Okay, so my answers though, I get a negative 1/2. Well, that doesn't make sense. I can't have a rate that's negative, so my rate is 8. Let's go back and remember what that means. R is 8. R was the speed she was going by herself before she had to add or subtract the current. So really, we've got the answer. 8 is our answer. Stephanie can paddle 8 kilometers per hour in still water. So that's my answer. Okay, I've tried to do a couple of each type. If you pay really close attention, take good notes, the 6 problems you have for your homework should be super similar to the ones that we've done here. All right, good luck.